Hello, my name is Catherine Nguyen. I'm a student at Old Dominion University and am completing a series of demonstration videos for microcontrollers and embedded-based designs as part of my senior project. In this video, I will demonstrate the operation of lab number 8, SPI data logging with temperature sensor readings in C. This lab utilizes the built-in LCD connections on the trainer board to interact with the provided LCD module. Additionally, an external EEPROM is implemented on the trainer board. Data, clock, and chip select lines can be accessed via X9. This lab requires two separate source codes to be written. The objectives of Part 1 include reading real-time temperature values from the sensor using I2C, logging readings into the E-square using SPI, and converting the data to values ready for display on the LCD. Part 2 requires that the logged values be retrieved from the E-square using the second source code. As in Part 1, the readings must be converted for display on the LCD. Note that the readings here are in degrees Celsius. For reference, room temperature is generally between 20 and 25 degrees C or 68 to 77 degrees Fahrenheit. The LCD, EEPROM, and temperature sensor are implemented on the board, so all that is required is to add jumpers between the appropriate terminals and add in a few resistors for the I2C connections. As always, double check that your switches, namely S1 and S4, are configured correctly based on the number of pins on the PIC you are using. Reference the appropriate manual for the revision of the trainer board you're using if needed. I'm using the 16F877A with a Rev 3 trainer board and have S1 1 to 5 on and 6 to 10 off. For S4, I have 1 on and 2 off. Oscillator connections are required for this lab. The connectors share a terminal with port E for this PIC and are connected directly to the oscillator circuit implemented on the trainer board via SV4. The LCD will need to be inserted into SV1 and connections made from the X29 terminals to PIC I/O. In this case, 8 lines from port B are used to control the LCD. Next we have the register select and enable lines. I have used 2 pins from port C to control these lines. Finally, the voltage reference and read-write lines must be connected. The voltage reference required varies by LCD module, and you will need to verify what's needed for your specific LCD. In my case, the voltage reference and read-write lines are connected to -5 volts and ground respectively. Connections to 5 volts and ground are required for the I2C interface, so the breadboard buses are wired to facilitate these multiple connection points. SPI connections are made between port C and the X9 terminal, which is connected to the external E-square. As with other components implemented on the board, connections directly to power and ground are already taken care of. SPI and I2C are sharing output pins for the data and clock lines. For I2C, both the data and clock lines are tied high using 10K resistors. I2C connections are made between port C and the X31 terminal. As discussed, the data and clock lines are shared. The breadboard rows are used to facilitate these connections. The addressing pins A0 to A2 are tied to ground, and +5 volt in that order. The program is set up such that it will begin reading, logging, and printing converted temperature values as soon as power is applied. Readings occur approximately every 5 seconds. The sensor will be allowed to capture room temperature for the first few readings. I will carefully touch the top of the sensor to cause the temperature to increase, and as expected, the temperature increases from approximately 27 1/16 to 30. After I move my hand away, the temperature begins to decrease. I also have a hemostat that was chilled with an ice pack that I will touch to the top of the sensor. Any metal implement that could be placed in the freezer or chilled in another way would work similarly well. Here the temperature readings show that the temperature is lowering slowly. Once the hemostat is moved away, the temperature increases for the final reading. Once Part 1 is complete, the power is removed from the circuit and the PIC reprogrammed or swapped for another with Part 2 loaded onto it. As soon as power is applied, the Part 2 program will begin to retrieve the values logged in Part 1. These values are converted for printing again as done in Part 1. The resulting temperature values in Celsius are printed on the LCD for comparison with the Part 1 results. These values should match the values from Part 1 exactly. I have overlaid the results from Part 1 for easy comparison on screen. Resetting the circuit or removing power should not alter the values displayed, as they are being read directly from the E-square. As in Part 1, due to space constraints, I've had to clear the LCD to continue printing the readings. After the 10th value is retrieved, my program will print a done to indicate that all values have been retrieved from the E-square. E-square paging issues were not addressed in this demonstration because there was no requirement to use a particular address range. However, page limitations are critical and are discussed with a brief experiment following the references. This concludes the demonstration of lab number 8. Please see the associated documentation for additional information and instructions. The program shown is configured to write 10 consecutive ASCII values representing 0 to 9 to the external EEPROM at the beginning of the specified address. The ASCII characters are also sent to the LCD as they are stored. Because there are only 10 values stored on a page of 64, if the writing starts at hex 0, there is no paging issue, and all the characters that were written are retrieved. Here the retrieved values displayed match the stored values displayed previously. For the second run, assuming a page size of decimal 64 or hex 40, I will write to hex 37 so that one character will be written to the start of page 1 as the write wraps across the page boundary. Here I'm holding reset while I rebuild the project and reprogram the PIC. I've only altered the start address for reading and writing so the same values are stored. However, beginning the write at hex 37 means that the last value will not be stored sequentially. So here there is a lowercase y with umlauts as opposed to the 9 that would have been written if not for the paging issue. This value was pulled from the first address of the second page by the sequential read. Similarly, beginning the write at hex 38 results in two characters being written to the beginning of the first page rather than being written onto the second page where the sequential read would have retrieved and printed them. I make this adjustment here and reprogram the PIC. Again, the stored values are the same, but the retrieved values will help display the paging issue. And after a brief delay, the retrieved values will again show that items cannot be written across the page boundary sequentially. The last two retrieved values here are from the second page, which we were not able to access in the original sequential write.